Let's get a sketch of this device when the face of this cylinder is out there at point B. So I'll draw the tube. I'll put a point B right there. Draw my cylinder in it. It's got a mass M, and then in this case the spring is stretched. Point A is the point about which everything is rotating, and we'll say that it's stretched an amount, goes from here out to there. I'll call that a distance x. I think x is given. So front face, okay, if it moves from here to there, it moves a distance 6 centimeters, then the back face has to move the same distance, and how far the back face moves is how far the spring stretches. So this is x right here. So equals, I'll call it 0.0600 meters. I'm going to solve the problem first, and then, as if I didn't have to worry about the error analysis, and then I'll go back and do the error analysis afterwards. I won't say separately, but I use the results that I learned in this case to get those. Alright, what else? The thing is rotating. With a speed omega. Omega is given as 960 revolutions per minute. And there are 2 pi radians in a revolution, so I'll multiply that by 2 pi radians per rev. And a minute is 60 seconds. So that's another 1. Both of these ratios are 1. And I wrote it so that the minutes would cancel out and the revs would cancel out. And I get a value for omega in radians per second. And I get 100.5. radians per second, which makes sense. 2 pi is around 6 divided by 7. That'd be 1/10 of this, which would be about 96, except the 2 pi is a little bigger than 6, so that checks. So I got a value for omega. Let's see what else I need. I need to know how big this circle is that this cylinder is moving on. I'll go to the center of mass of the object. I'm going to call that R, lowercase r. And let's see what else they give me here. They give me the length of the cylinder. I'm going to need half that length to figure out what r is, so let's put that in there. This is lowercase l, I'll call it, and it's it's 2.5 centimeters. Yeah, cylinder of length 2.5 centimeters. So 0.025 meters for the length of that cylinder. Okay, again, I'm trying to get r, and let's see what this is. B is 13.4 centimeters out. So this distance out from point A, I think I'll call that D, and it's equal to 0.134 meters. Okay, I'm feeling good about this now. We got r, the distance out to the center of mass, is just going to be d minus L over 2, or 0.134 meters minus 0.025 meters. So I need to know the radius of the circle that this object is spinning on when the face of it is all the way out there at point B. And this is an expression for it. So this is, did I finish that? That's over 2. I did not. It is over 2. And now I go ahead and evaluate that, and I get 0.125. I'll keep some extra sig figs. We're going to actually do full-blown error analysis on this, so we don't have to worry that much about sig figs. We'll figure out how many we should be keeping at the very end based on the error analysis. Okay, so the idea is this device is spinning around. As a result, the spring extends, so the mass is out there at point B moving around in this big circle, and in order to do that, the force exerted by the spring has got to be consistent with the acceleration of the object. And the acceleration of the object, it's experiencing a centripetal acceleration. I'm actually going to view this from the side. So this is a top view. I'm going to view it from here. View from point, call that point C. Side view. So I'm at point C. The top of my, you're looking down on me. The top of my head is all you can see, and my shoulders. If I were at point C, and that's my point of view. I'm calling it a side view. From that point of view, out of the page here would be up here, so that'll be a normal force acting up and a weight acting down. It was really so I could get these forces in that we're not using. Even though we're not using them, I wanted the free body diagram to be complete. Here's an F sub S, the spring force acting on it, and we've got some acceleration, which is the centripetal acceleration acting in this direction. And in fact, that's going to be equal to, from your formula sheet, you can determine that it's just r omega squared, where r is the radius of the circle that it's moving on, this r that we went to such great pains to determine, and omega is how fast it's spinning. Okay, we can sum the forces to the left in that diagram, set it equal to the mass times the acceleration to the left. Only force to the left is that spring force, and the acceleration is indeed to the left. I use the symbol A to represent that. So rather simple application of Newton's second law when it comes down to that part, but Kx, this is the spring constant times the amount of stretch, and that is the spring force in magnitude, and I'm only worried about the magnitude here, so I'm not writing any minus signs, for instance, and it's equal to the mass times r omega squared. So K, the spring constant, which I believe is what they're asking for, what spring constant is required? K is just mr omega squared over x, which is equal to the mass is 0.118 kilograms. R we found to be 0.1215 meters. Omega we found to be 100.5. Radians per second. That does have to be squared. In fact, there it is. And X was given as 0.0600 meters. I evaluate that, and I get K is equal to 2413 kilograms per second squared. Kilograms right there, per second squared, and the meters cancel out. And radians, remember, not a true unit, more a marker than a unit, and I can erase that and get my result for K. Alright, that is the result for K. I need to get it with error, so I'm going to go back to, I'll call this, let's call that equation 2. Yeah, I think that's going to be a 3. I'll call that equation 3. So equation 3 reads, I want to call that one 3K is mr omega squared over X, the one I was just working with. And I want to see, M was given, so I can use that directly. R was not a given, so I want to use the expression that we had for that. So I'll call this 2 and substitute 2 into that. So I get K is equal to M D minus R over 2. I'm sorry, L over 2, because these things were given. L and D were given. I want to get this all in terms of givens as opposed to things that I calculated for. And omega was given as in terms of omega RPM, I'll call it. It was given in different units. I'm going to define this to be omega RPM. And I'll call this 2 pi radians per rev constant C1 and this one constant C2. So I'm going to call that equation 1. So substitute 2 and 1 into this. So for omega, I'll have omega RPM times C1 times C2. And on the bottom I've still got X. Okay, I need to substitute values with units and error in there. I'm going to use GALCP to do that, and I want to make a table here of the values that I need. So I need the mass, which was given 0.1180 plus or minus 0.0020 kilograms. Just convenient, real convenient to make a table here, so when I get to GALCP I know exactly what to substitute in there to type in. And this is 0.134 plus or minus 0.0020 meters. And then I've got, let's see, L is equal to 0.0250 plus or minus, that's the lowercase l, plus or minus 0.0010 meters, and omega RPM given as 960 plus or minus 18 revolutions per minute. And finally, X was given as 0.0600 plus or minus 0.0020 meters. And the C1 and C2 that appear in there are exact values. C1 is exactly equal to 2 pi radians per rev, and C2 is equal to 1 over 60 exactly minutes per second. So I just have to use Gal-CP, substitute all these values into this expression, and within Gal-CP to determine what K is with error. I'm going to do this on a second part to this WinCam, so I'm going to close this one out here, and then I'll just say view part 2. Maybe to be nice. Please view part 2.